Hi everybody, I'm Mathieu Aubry and I will be presenting the speaker for this section. Together with Derek Oem, who will probably be joining us during the session. Just an announcement before we start. Could all the spotlight speakers to come to the front and sit on their seats so that we can check their role here. And so there will be 4 roles in this session, and after every role there will be questions. So if you have a question to ask, please come to the microphone in the middle of the room. Okay, so our first paper is a SPLATNet, Splat Lattice Network for Point Cloud Processing, and it's one of the honorable mention paper. And it will be presented by Ming-Hsuan, and it's a paper with Varun Jampani, Deqing, Subhransu Maji, Evangelos, Kalogerakis, Ming-Hsuan Jiang, and Kautz.
Thanks for the introduction. It is my pleasure to present SPLATNet, our work on point cloud processing. And it is our great honor to receive a Best Paper Honorable Mention Award at this CVPR. Point cloud is a very common way of representing 3D information for applications like robotics, autonomous driving, and also graphics applications. Therefore, techniques for processing them directly are becoming increasingly important. Despite the exciting advances in deep learning for images, learning from point clouds is still a challenge because they are not a good fit to standard CNNs, which are designed to operate on dense, regularly structured data. There are a few widely used workarounds to perform 3D deep learning. Many resort to voxelization, where discretization step put data on a dense, regular grid so standard 3D convolution can be directly applied. Another common choice is to use multi-view 2D projections, where 2D projections are considered instead of the 3D objects themselves. Although with their own strengths, these workarounds suffer from artifacts and loss of details, or are computationally expensive. There are some recent work on networks that can directly operate on point clouds to avoid those issues. KD networks build KD trees on the points and then perform filtering on the tree nodes. PointNet and PointNet++ process individually and then aggregate information globally or hierarchically using max pooling. Similar to those approaches, we also design a deep learning architecture for direct point cloud processing. There are 2 key capabilities that we found lacking in previous work and that we emphasize in our design. The first one is a flexible specification of filter receptive fields. It is well understood in 2D CNNs that using different filter and receptive field sizes allows capturing information at multiple scales. This can also benefit understanding 3D shapes. For example, for the airplane shown here, while a smaller receptive field can capture its tail and engine, a larger receptive field is better suited for capturing the shape of the wings. The second capability we'd like to bring in is the seamless integration of 2D, 3D information for joint processing. Many sensors output 3D data and 2D images simultaneously. Images can provide complementary information to 3D data and also allow us to leverage powerful models and architectures developed for image understanding. I will revisit these 2 points later and explain how they are achieved by our network design. But before then, I will introduce bilateral convolution layer, or BCL, and how we make use of it on 3D point clouds. BCL was originally proposed by Jampani, my co-author, and Kifo as a generalization of bilateral filtering. For us, BCL provides a way to filter sparse and unordered points efficiently. There are 3 steps in a BCL unit. In the first step, called splatting, points are interpolated onto the vertices of some lattice structure. Then convolution is performed on the lattice vertices. And in the final step, called slicing, filters the signals are interpolated back onto the original set of point locations. BCL provides good computational efficiency. Permutohedral lattice is used as opposed to regular grid because the number of neighborhoods grow linearly with the number of dimensions as opposed to exponentially. It is more scalable to higher dimensions. This is particularly important for processing 3D point clouds where there are often actual feature dimensions beyond XYZ, like normals and colors. BCL also makes use of hash table to restrict computation to only occupied vertices. This can significantly save computation for sparse point clouds. What's unique about BCL is that it allows specification of 2 sets of input features. The first set of features, point feature, represent what is observed at each data point, while the second set of features, lattice features, tells us where the points are in the space. Let's take 2D image filtering for an example, which can be seen as a special case of BCL. The point features are the RGB colors, and the lattice features are simply the XY location of the pixels. To filter 3D point clouds, in the simplest case, we can use occupancy as point feature, which is always 1, and use the XYZ location of each point as lattice feature. Alternatively, we can use the point location as both point feature and lattice features. And now we can really see the flexibility here when we choose to use RGB color as point feature and both XYZ and normal directions as lattice feature for a 6-dimensional filtering. For both image and point cloud, the point feature can also be arbitrarily dimensional feature generated by previous network layers, allowing BCL to be used in deep neural network architectures. The lattice features can be defined on lattices of different scales. This allows us to control the receptive field during convolution. For example, in this figure, the same set of points are projected into lattices according to XY locations at 3 different scales. Assuming we're using the same filter neighborhood size, coarser lattices correspond to larger receptive fields without increasing the number of learnable parameters. Let's see another example in 3D. Here we are visualizing the point clouds so that all points belonging to the same lattice cell are in the same color. On both sides, XYZ is used as lattice feature, but on the right, the lattice is 8 times finer. We can see that by simply using a different lattice scale, we achieve finer discretization of the space. Another useful property of BCL is that input and output can be at different point locations. In earlier examples, the information was filtered back onto the original point locations in the slicing step. However, we can instead slice at a different set of locations, here depicted as the green dot. We make use of this capability to seamlessly integrate 2D and 3D information in our network. As an example, let's suppose there are some 2D pixel features, F, here illustrated as the pixel colors, and we want to get those features onto a point cloud. Assuming that for each pixel, we also know its corresponding 3D location XYZ, we can easily use F as point feature and XYZ as lattice feature, splatting the 2D features onto a 3D lattice space. And in the slicing step, we can output at the actual point cloud location to gather features for the 3D point cloud. Later, I'll refer to this BCL variant as BCL 2D to 3D. Similarly, we can do the reverse and smoothly project information from 3D point cloud to 2D images. Later, I'll refer to this as a BCL 3D to 2D. Now that I have covered the building blocks we need based on variants of BCL, I will proceed and introduce our network architectures. Given the 3D point cloud as input, we are solving a segmentation task to give each point a label prediction. When there are 2D images available depicting the same object or scene, the task is to do learning and prediction jointly, improving both 3D and 2D predictions. Here are the internals of 3D version of our model. Let's walk through the components one by one. The input points are first processed through a point-wise convolution layer, which is denoted as 1x1 conv. And then there are a sequence of bilateral conv layers. Here we assume all BCLs use XYZ as lattice features, and each has increasing lattice scale as noted at the bottom of each block. And as illustrated above, this has the effect of gradually increasing the receptive field of the network. Similar to hypercolumn, we concatenate the output from all BCLs and finally output 3D predictions after a couple more 1x1 conv layers. For the joint 2D 3D version of our model, we'll use 2 more building blocks introduced earlier, BCL 2D to 3D for projecting pixel-wise information onto the point cloud, and BCL 3D to 2D for the reverse. Here are the internals of SPLATNet 2D 3D. Again, let's walk through the components one by one. The 3D network is included as part of the joint network for extracting 3D features. From 2D images, we first apply a 2D CNN to generate 2D image features, which are then projected onto the 3D point cloud and concatenated with the 3D feature from the 3D network. after 2 additional 1x1 conv-layers, we can get predictions for the point cloud. And on the other path, the signal is projected back onto 2D pixels, concatenated with earlier 2D image features, and then pass through an additional 2D CNN before finally predicting 2D labels. I'll now present our experimental results. The first benchmark we evaluated on is RuMonch 2014 for building facade segmentation. Here is the testing sample, the ground truth labels, and our predictions. Quantitatively, on this benchmark, SPLATNet 3D improves upon previous state-of-the-art voxel-based method and traditional vision methods by a significant margin while having competitive runtime. Using our joint model, the IOU is further increased, showing improvement over previous joint methods on this benchmark. Our joint 2D3 model also helps improving 2D predictions. Here, the second column is the ground truth, and the third column is our prediction. In the table, we can see that while the 2D CNN we trained with images only is already very strong, our joint 2D 3D model using the same 2D CNN as backbone achieves additional improvements. Another benchmark we evaluated on is ShapeNet par segmentation. Quantitatively, our SPLATNet 3D is on par with the state-of-the-art methods, and our joint 2D 3D model achieves further improvements. All 3D bilateral conv layers shown previously in our network use XYZ with different scales as lattice feature. We also investigated using a 6-dimensional lattice feature, XYZ, and point normal directions. However, doing so only improved performance marginally. Using different lattice feature space can allow points to interact in different ways. For example, here in the second figure, when using normals as lattice feature, points on the wings, although very far away spatially, are considered close by and thus can easily interact in the network. Although our experiment doesn't show large improvements, we believe this is a valuable capability, and we hope it can inspire future research. To wrap up, we present variants of our model, SPLATNet, which allows efficient computation directly on point clouds and flexible specifications of filter-receptive fields, and also seamless joint 2D 3D processing. Our code is available online, and also welcome to see us for more details in the post session. Thank you very much.
Thank you. Are there any questions? Can you go to the microphone?
Hi, have you compared with the EdgeCom, the dynamic graph network, which they do computation on the edges, and then you can basically have larger and larger local features?
Yes. So that work, I believe, comes after our submission, and it's very related to our work in the sense that it can also define a neighborhood depends on some learned features. So we didn't do any comparison, but in terms of idea, I believe this is a very similar kind of work.
Okay, thanks.
Thank you. We have time for another question. So if not quickly, so it seems your network is not invariant to rotation. So do you have a notion of how invariant it is in practice, or how you can make it invariant?
So like quite a few recent work on 3D deep learning, we don't have any rotation invariant built into our model. But it's easily achieved if we can just chain models with perturbation with different orientations. And this is what we did in our chaining. So we do random perturbation for rotations, and this can help a little bit for rotation invariance. But some of the benchmarks are set up in a way that this actually hurts testing performance. So this is, I think, an issue for current benchmarks.
Thank you. Let's thank the speaker again. And our next speaker is Ilya Kostrikov, and he will be presenting a paper called Surface Network, written with Zhongshi, Jiang, Daniele Panozzo, Denis Zorin, and Joan Bruna.
so just have network connections. Okay. My name is Kostrikov. Today I'm going to present our paper called Surface Networks. It's a joint work of machine learning and graphics groups at NYU. In this work, we introduce a neural network for 3D surfaces based on an extrinsic geometry operator. For this model, we use a regulated mesh representation for surfaces instead of point clouds or graphs. Then we present an application of this model for surface dynamics predictions. In this task, exact commutations can be expensive and can be beneficial to use a fast approximation. Also, we introduce a surface generative model based on the variational autoencoder. And finally, we prove certain stability properties of the model described in the paper. First, let me summarize some prior work on the topic. As I already mentioned, surfaces can be represented as point clouds. In this case, for machine learning applications, one can use models defined on sets, such as PointNet, memory network, communication network, or the model that was presented during the previous talk. These models use some operator that aggregates global information, such as tensor or simple maximum or average pooling. Another possible representation is graphs. In this case, one can use graph neural networks. A layer of graph neural network can be defined the following way: given some signal x on the nodes of a graph and some local operator, we can apply this operator to the signal and then multiply by some weight matrix and then apply some nonlinearities. For example, one can use the Laplacian operator and the identity operator, as you can see on the slide. Also, one can apply standard neural network layers such as pooling and nonlinearities. Originally, graph neural networks were defined for a signal on nodes of a graph, later inspired by message passing algorithm. These methods were extended to the signal on edges, as well as alternating between edges and nodes. Nonetheless, these methods can capture certain geometric information. In this work, we consider another representation of surfaces. A triangulated mesh consists of a set of vertices connected by edges that form faces, and we would like to use all these components within a neural network. As I said, in this work, we introduce the Dirac operator. Dirac operator, in contrast to the Laplace operator, is an extrinsic operator. This operator is defined for surfaces, and a discretization of this operator for a triangulated mesh can be defined in the following way. It's edge vector embedded into the quaternion space, normalized by the double area of the surface, or sorry, of the face. The operator is defined with quaternions. On the following slide, I will explain how to combine this, how to use actually quaternions within the standard graph neural network framework, and how to implement this in popular deep learning libraries. Also, it's worth mentioning that on general graphs, there is no notion of square root of the Laplacian that recovers orientation, as opposed to Euclidean domains, where the Laplacian is given by the divergence of the gradients of a function. The Dirac operator defined here generalizes the gradient operator on surfaces and is a discretization of the original operator that arises in quantum mechanics. Therefore, in the case of surfaces, neural network that use the Dirac operator is a strict generalization of graph neural networks based on the Katangian Laplacian operator. They can at least perform the same transformation of the input signal as the Katangian Laplacian based neural networks. As I said, the operator is defined in quaternions. However, in most deep learning libraries, it's more convenient to work with real tensors. Fortunately, the quaternion can be represented as a 4x4 matrix, and then we, in order to apply the operator, we just perform standard real-valued matrix multiplications, and then we can define a layer of neural network in the following way. Given some signal on vertices, we apply the Dirac operator and then multiply by some weight matrix. And for the signal on faces, we apply the adjunct operator. So basically, when we use the Dirac operator, it alternates the signal between vertices and faces. Oh, and also it's worth mentioning that inputs are also embedded in the quaternion space. Okay, we evaluated the neural network based on Dirac operator against several other models. The first model is a neural network that doesn't aggregate any information, can be seen as a one-by-one convolutional neural network on graphs. The second model uses global average pooling, and finally we evaluate it against a standard graph neural network with the Laplacian operator. For all models we used a similar architecture. We used the layers described on the previous slides combined with the widely used ResNet architecture. For the Laplacian global average pooling, it's more or less a standard ResNet model, but for the Dirac operator, since it alternates between nodes and faces, we used scheme connections only for the signal of the same type. For variety applications in computer graphics, it's sufficient to use intrinsic operators or don't use graph neural network at all. For example, one can just render, for example, for shape classification, one can just render like different views of a shape and then classify it. Therefore, we introduced a new data set. I can just show some videos from this. So basically, this is the data set for dynamics prediction. Given like some shape, we just give it a fall to the ground, and then using a simple technique model the dynamics. The dynamics here are deterministic given several initial frames of a sequence, and it allows us to use a simple smooth L1 loss instead of a complex latent variables model. So Dirac plus operator performs significantly better than the point cloud model, and as you can see, the Dirac operator also performs better than the Laplace-based model. On these images, you can see that the Dirac operator performs better in the regions of high curvature. Okay, let me skip the slide. Also, we introduced a imaginative model. For this task, we created a simple data set based on MNIST. We constructed in the following way. We generated 2D meshes and then used intensities of pixels from the MNIST data set to define height field. The generated model consists of two parts. We take this 3D mesh and project it to 2D. And then we use an encoder to produce a latent vector. Then we decode it, taking the flat 2D mesh and the latent vector. As in the standard variational autoencoder framework, we have a reconstruction loss and Kalogerakis between the latent vector and some simple distribution. In order to generate a new 3D mesh, we sample a 2D mesh using the same procedure and the latent vector from some prior distribution, and then use the decoder to obtain a 3D mesh. This model disentangles mesh and later representation. On the left side, you can see that it produces similar results for different meshes and the same latent vector. And on the right side, it produces different results for different Z vectors. In principle, the model can be extended to more difficult cases. For example, for genus 0 shapes, one can first map the shape to a surface or to a sphere, and then restore it from sphere. Also, in this work, we study the stability properties of the representation with respect to deformation and discretization. We want this representation of the mesh to change little if you apply small deformation to the input, or if you remesh the same surface. The first theorem shows that a small non-rigid perturbation produces a small change in the network features, both in the Laplace and the Dirac case. Difference in norms corresponds to the fact that the Laplace operator is isotropic, whereas the Dirac operator is not. The second theorem shows that two different discretizations of the same surface produce features that are close provided the mesh is a good approximation of the surface. In the sense of uniform normal distance. The second result requires the input signals to be smooth in the sense of Sobolev, and we believe that this assumption may be significantly weakened. Okay, so in conclusion, we presented a neural network based on the Dirac operator that is defined on a triangulated mesh. The Dirac operator is an extrinsic anisotropic operator that can capture principal curvature directions. The model has been applied to raw coordinates and doesn't require any handcrafted feature descriptors. We rated it on surface dynamics predictions and introduced a generative model for meshes. We also provide We also prove certain stability properties of the model described in the paper, in particular stability properties of the representation with respect to deformation and discretization. Okay, basically that's it. Thank you.
Thank you. Are there any questions? So if you have questions, please go to the microphone.
Hello. So when you compute the Laplacian, what kind of discretization method and boundary condition do you use? And also, are there any requirements on the surface mesh? Does it have to be a closed surface, or any open boundary surface will be fine? Thank you.
Excuse me, I could you repeat the first question? With respect to the quality of the meshes, we actually noticed that it's extremely important to have like a really good mesh, because if like you have like any problems, any holes, like any like doubled vertices, it works really poorly. And also, yes, what was the first question?
So what kind of a boundary condition do you use? Like
we use no boundary conditions.
Okay.
We have time for a second quick question. Do you have an idea about how to extend your method to point cloud?
For point clouds, one can locally estimate. For point clouds, one can estimate like faces locally, and then just apply this like operator to this local estimates of like faces and vertices, and yeah, basically that's it.
Thanks a lot. Let's thank the speaker again. And our next speaker is Ayush Tewari, and he will be presenting a paper called Self-Supervised Multi-Level Face Model Learning for Monocular Reconstruction at over 250 Hz. And it's a joint work with Michael Zollhöfer, Pablo Garrido, and Florian Bernard, Yegu Kim, Patrick Perez, and Christian Theobald. Thanks.
Right. Hi. I will be talking about our self-supervised approach for learning a multi-level face model. Here is the goal of our approach. Given monocular input images of faces, we want to obtain 3D reconstruction of these faces. And these 3D reconstructions are defined as the 3D facial geometry of the face, as well as the appearance of the face in terms of the skin reflectance and the scene illumination. Going from a single monocular image to all these different channels of reconstruction is very ill-posed and challenging to solve. Because of the challenging nature of this problem, 3D morphable models have been proposed in the literature. These morphable models capture different modes of deformation for both facial geometry as well as the skin reflectance. These deformation vectors are usually computed from high-quality 3D scans. As such, they form a well-defined prior for these reconstruction tasks. However, it's time-consuming and expensive to scan a large number of faces. And in addition, it's quite difficult to scan in the wild faces, for example, ones with facial hair. Because of such reasons, these morphable models do not generalize very well to in the wild faces. There have been a lot of works which, based on 3D MMs, which try to perform this task of face reconstruction, but since they limit themselves to the subspace of these models, they do not work very well in the wild. There have been a few works which try to go beyond these morphable models in order to capture more general faces, but even these approaches do not scale very well to thousands of different identities. And these approaches typically try to refine either the geometry or the appearance part of the reconstructions without looking at them in a joint fashion. In our work, we learn a multi-level face model from monocular images. This is a model for both shape and reflectance. This model has two different submodels. So the first, we have a base model, which lives within the 3D space I described before. Given some low-dimensional parameters, it gives us the reconstruction at the base level. In addition, we have a learnable corrective space. This corrective space captures the out-of-subspace variations which are not present in the base model. However, they are present in the monocular images. Including the corrective space, we get a reconstruction at another level, which we call the final level. Since we need only monocular images to train this corrective space, we do not need any further scans in order to learn this model. In addition to learning such a face model, we jointly also learn the task of reconstructing faces. And finally, our pipeline allows us to perform this face reconstruction task at really high frame rates. Let's look at the pipeline of our approach. At training time, our network receives monocular input images. We then have a convolutional encoder which transforms these images into parameters of our face model. The model, as I described before, gives us the reconstructions at two different levels, the base level and the final level. Once we have these reconstructions, we have image formation layers, which projects these reconstructions to the image plane and gives us a synthetic image. So these are rendered image corresponding to the reconstructed faces. Once we have these renderings, we have a loss function which compares these renderings to the input images, and the network uses this loss function in order to train the trainable components of the network. Note that all different modules of this network are differentiable, and thus we can use backpropagation to train our models. Let's look at our network in more detail. We first have the convolutional encoder, which is the regressor for model parameters we use. In our work, we use AlexNet as our encoder, but any other regressor or CNN could be used for this task. The encoder first gives us some common scene parameters. These, first of all, we have the rigid pose in 3D, which is described using 6 numbers. And we also have some parameters which describe the scene illumination, and these are the coefficients of the spherical harmonic basis functions. Then we have the base model, which in addition receives some more semantic parameters. First of all, we have some parameters for the 3D morphable model I described. So we have some for the shape component, some for the reflectance, and using this 3D we can recover the identity part of the reconstruction. In addition, we use an expression model, which captures localized shape deformations of the face corresponding to different expressions. And we have a few parameters, 64 here, which are for the expressions. The output of the base model is the per vertex reconstruction of both the facial geometry and the skin reflectance. Note that this base model, both the 3D and the expression model, are completely fixed and not updated during training. Here you see some reconstructions obtained using just the base model. We can obtain nice reconstructions, but they're not high quality or very personalized to the input images. This is why we add our corrective space. This corrective space will try to capture the outer subspace variations which are not present in the base model. It itself is modeled as a neural network, which as input receives again some low dimensional parameters for both geometry and reflectance, and as output gives the per vertex correctives for again both the components. Note that we have two separate models to capture the geometry and reflectance of the face. Here you see a comparison of using just the base model for the reconstruction compared to using the corrective space as well. So you can see that the corrective space indeed brings us outside of the morphable model space and gives us higher quality reconstruction for both the components. Then we have the image formation layer. The image formation layer first computes the 3D model of the face from the geometry and reflectance it receives and also the scene parameters. And once it has the 3D model, it does a perspective transformation, projects it to the image plane, and gives us a synthetic image of the reconstruction. This image formation layer, like the base model, is fixed and not trainable. Finally, we have our loss function to compare the renderings to the input image. This loss function has 3 components. First, there's a dense photometric alignment term, which for each vertex of the reconstructed mesh tries to align it to the corresponding pixel of the input image. We have a landmark alignment term, which tries to align some automatically detected key points on the input image to the corresponding key points on the reconstructed mesh. We also have some regularizers. First, we have some statistical regularizers on the parameters of the base model. These try to ensure that these parameters are not too far away from their mean value. We also have a Laplacian smoothness term on the geometry correctives to ensure that the final reconstructions we obtain are smooth. We have a couple of reflectance regularizers. The first one tries to ensure that the reflectance changes in a sparse manner on the face. And we have another global term which tries to make sure that the reflectance values in different skin regions of the face are similar. These 2 terms tries to distinguish the reflectance part from the scene illumination. Finally, we have a stabilization term which tries to ensure that the final reconstructions we obtain are not too far away from the reconstructions obtained at the base level. Using such a loss function and a training data consisting of only monocular images and some automatically detected key points, we train our models, and here we look at some results. First, see the input image, the reconstructions we obtain overlaid onto the input image, the reflectance, geometry, and illumination channels of the reconstruction. We can obtain nice reconstructions in the presence of makeup and facial hair. We can capture geometric deformations, including those of eyelids. And we can also capture high-quality personalized nose and lip shapes. Even though we train our approach only on monocular images, it works quite well even on video sequences like the ones you see here. Note that our approach allows us to track these videos at really high frame rates at over 250 frames per second on a standard machine. Okay. So here's a comparison to the approaches of Richardson and Sela et al. Most of the methods in such challenging cases with facial hair and skin makeup fail to obtain plausible reconstructions. Our method can achieve high-quality reconstructions even in such challenging cases, and in addition, also recover the appearance of the face. We also compare to the approach of Garrido et al. Garrido et al. Try to go beyond the 3D morphable model in the geometry dimension by using a fixed set of correctives, which are the spectral harmonic basis functions. We show that by training an optimal set of corrective bases, we can obtain higher quality geometry reconstructions, and in addition, also model the correctives for the appearance dimension. We are also orders of magnitude faster than this approach. To conclude, we show how to learn a multi-level face model from just monocular images. The model consists of a base model for regularization of the training and a corrective space to capture the outer subspace deformations. We jointly train for the task of face reconstruction, which allows us to perform high frame rate reconstructions at test time. And finally, we provide a general framework which could be used for learning 3D models of other objects from images as well. Thank you.
Thank you. Any questions? So I have a question. So do you have idea if your model can be extended beyond faces, or what's lacking to extend it beyond faces?
So currently, for regularization, we use a base model, which for faces is quite nice. We have a 3D morphable model for both shape and appearance. So if you want to extend exactly this approach to other objects, you would need such a model. So for objects where we have such models, for example, for bodies, I think we have models for shape. I think it could be extendable. For other objects, I think it's probably not directly applicable, but it would be interesting to see how much of this regularization we need as a base level.
Thank you.
If I understood correctly, then you do not really render the images, but you only project them. Is that correct?
Yes.
So your error works on the is computed on the vertex color.
Yes.
So how do you cope with self-occlusions?
So the occlusions are not differentiable. I mean, we just so the loss is per vertex, and we calculate which vertices are not visible for the current case for this particular image in the batch, and if it's not visible, we do not consider the loss.
But how do you compute that they are not visible?
I mean, there could be smarter ways, but currently we just say that if the vertex is back-facing, it's not visible. But you could, in theory, render a depth map and check it if it is visible or not.
Right.
Thank you. Let's thank the speaker again. And our next paper is presented by Michael Block. It's called Code Slam, Learning a Compact Optimizable Representation for Dense Visual Slam. And it's a joint work with Jan Czarnowski, Ronald Clark, Stefan Leutenegger, and Andrew Davinson. And it also received an award.
Thank you very much for the introduction. So in this work, we are going to explore the intersection between deep learning and SLAM. And in particular, we are going to explore what kind of representation that we can learn in order to do dense SLAM, dense visual SLAM to be precise. So if we have a look at what representation have been used in visual SLAM, we can basically categorize them into two groups. On one side, you have the sparse methods, which parameterize the environment through a sparse set of key points. And that comes with a very compact state, a small memory footprint. But even more importantly, that comes with the ability to jointly optimize for motion and geometry. On the other hand, you have dense representation. And dense representation comes with a much fuller representation of the environment. And examples are dense point clouds, TSDFs, voxel grids, or meshes. And another advantage that they come with as well is that they can exploit, theoretically, more information from the image. And what we will try to do is basically to take the advantages a bit from both worlds. So we are going to investigate depth maps. And this is a depth map from the CNET RGBD dataset. And if we just put next to it a random collection of values, we can see that a depth map is not at all a random collection of spatially uncorrelated values. But we do have like a certain amount of structure. And in other terms, this means that depth map basically live on a subspace of all possible set of values that we would have for every pixel. And for looking for such, sorry about that. Okay. For looking for representation for such subspaces, deep learning has shown that autoencoders are very powerful tools. And this is exactly what we're going to investigate. So in a first naive approach, you could think of like getting a big collection of depth data set and trying to autoencode them. Now, if we do this, and here we choose a bottleneck of around 100 dimensions, if we do this, we can only get like the biggest or the coarsest information through our bottleneck in the middle. But if we take one step back and again plot our depth map and put the image next to it, we can see that there is quite a big amount of structural correlation between both. So we can, for instance, recognize the table in both. We can recognize the sofa in both of these images. And this correlation is the extra point that we're going to try to leverage. So So we're going to propose to do the following network. On the bottom, you have the autoencoder I've mentioned before. On the top, you have the input image. And we will process this input image in a certain way, and then we call them features now, we'll use these features in order to improve the encoding as well as the decoding in order to get a better reconstruction. As a side channel, we also output the uncertainty. And the uncertainty is a very valuable quantity in SLAM, in probabilistic SLAM. Now you can also think of that network in a different way. If you take the path coming from the top left to the bottom right, this is basically depth from mono prediction, and this has been a very active field in the past few years. Now we have the extra advantage that we have this code in the bottom that allows us to modulate that depth from monocular prediction. So we train this network. We use a unit architecture for the image processing, which is inspired by previous work. We use a variational autoencoder for the depth encoding, and then we concatenate the layers from the top to the bottom network. We use only grayscale images, and we use a purely linear decoder. So there are non-linear activations, so we don't use ReLU, for instance, just for the decoding of the depth. I'll come back to this part later. Then we train this on CNET. We use a Laplacian loss in order to allow for self-supervised training of our uncertainties. We use an ADAM optimizer for 10 epochs. And we trained everything end-to-end from scratch. There are a couple of things I'd like to mention already when it came to the training. So we investigated different code sizes, and we saw that eventually we get like some kind of a saturation effect. So we get diminishing returns as we increase the code size. So we agreed on a code size of around 128 in the end. Two other things, and I've mentioned this before. So these are the training results or the reconstructions error when we use actual RGB or actual and nonlinear decoder, and we saw that we don't get any gain, meaning that this confirms our approach of using a linear decoder and only grayscale images. If we have a look at the results, so these are just 3 samples. On the left side, you have the input image, then you have the ground truth. Then in the middle, you have the zero code, which is nothing else than just plotting all zeros into the code and looking what the depth from mono prediction does. As fourth, you have the prediction where you get when actually encoding the depth. So you do see a significant gain over the zero code. And in the last column, you have the predicted uncertainty. And that's relatively interesting because it's really highlighting the depth discontinuities of our depth map. Now I'll come back to the linear decoding. So why did we choose a linear decoder? Using a linear decoder, the depth, which is a function of the code and the image, can be split into 2 terms. On the left side, you have the zero code prediction, and on the right side, you have just a linear term of the code. And given a specific image, so as long as we don't change the image, we call it the Jacobian, so the derivative of the depth with respect to the code is a constant term. So we can also visualize this. On the left side, you have the zero depth prediction, and on the right side, you have what happens if we perturb one single entry in our code. And one interesting thing to observe is that we basically get spatially smooth perturbation on our depth. And this is exactly the effect that we are going to leverage in order to build our SLAM system around that. So our SLAM system will have as degree of freedom the code, and it will be able to tune that code in order to do simultaneous localization and mapping. So how are we doing that in detail? So what we're doing is we follow a keyframe-based approach. So on the right side, you see 4 keyframes. And with every keyframe, we have a pose and a code. And these are our variables. Now we can retrieve the depth from the code by just using our network. So the depth is just a linear function of our code. And then in the second step, we are going to do dense bundle adjustment or photometric bundle adjustment. And what this does is basically pair ups keyframes, and then it warps the image from one keyframe into the other keyframe by using the depth, which is a function of the code, as well as the relative pose. And then if we have that warped image, we subtract the image and formulate the photometric error. And this photometric error is just a function of code and poses at the end. And we then jointly optimize for the pose and the codes, which is a thing that hasn't really been done previously in dense SLAM. So if we visualize this, so this is CNET, we pick 2 frames. So you have the depth and the image on the left. And this is basically the rendering as we optimize our network. Not the network, as we optimize our framework. And you see that the photometric error goes down. We also have a 3D visualization of this. So this is exactly, the left side is exactly the same example you've seen before. And we can retrieve relatively good reconstruction, at least for CNET here. We can iterate roughly at 10 Hertz. So really one of the boosts in speed comes from the fact that we can pre-compute the Jacobians because our decoder is linear. And we need around 20 to 30 iterations in order to converge. Now we've also tested this on different data. So here we tested it and applied it on a New York data set, which is a real data set. And we jointly optimized the 10 frames. So we start with setting all the poses to identity, all the codes to 0, and we basically jointly optimize everything. And then finally, we also turn this into a SLAM system, or visual odometry system. So here we have 5 keyframes in a sliding window mode, where we marginalize out all keyframes. And we've tested this on the NYU data set. And the colors here are just for visualization, so it's actually only using grayscale in the background. So I don't think that we can claim to perform as well as traditional approaches. I do think that there are a couple of things I'd like to mention. It's a relatively simple system in the end. So we have only one optimization problem, and as we start our framework, we start by just adding 2 keyframes. So there's no bootstrapping, there's nothing special. So we just have one optimization. Another interesting part is that we actually get some sort of prior from just plugging in the 0 code. And this is kind of robustifying the framework quite a bit. So we can, for instance, handle rotational only motion by having like this depth prediction, which we get without having any baseline. Yeah, so overall, I think we've introduced a new representation for SLAM. I think it's a very interesting direction, and it opens quite a couple of further direction. I think one important part to look into is how we can train this also on real data, maybe using self-supervised costs and not actually requiring depth. Other interesting thing would actually to couple it even closer to the optimization that we are doing afterwards. And there are plenty of other things. So you could do the network in different ways. You could enforce more structure on the network. So just before ending, I'd like to mention that Jan, my co-author here, has actually put together a demo, and he's going to demonstrate the system tomorrow live. It's a very preliminary system, but it works if the conditions are right. Yeah, otherwise, thank you for your attention, and I'd be happy to take a couple of questions.
Thank you. Any question?
Thank you very much. Very nice work. I have one question regarding how well your codes generalize to different types of scenes. Do you have any intuition there?
It's quite difficult. So basically, I think it's especially the 0 code prediction gets worse if it's not a scene from a similar data set. So that's definitely one thing which is less good. On the other hand, we have this optimization, which does allow basically to bend our representation to different type of scenes as well. I'm quite convinced that if we could actually train on real data, we would get better results.
Okay, thank you.
Any other question? If not, let's thank the speaker again. And we'll now move to the spotlight presentation. So if you have a spotlight, please be sure to be at the front and ready when your presentation comes up.
everyone. I'm Wei Wang from University of Southern Cal. Today I'm going to talk about 3D point cloud instance segmentation. What we want to do is given a 3D point cloud, and for each point, we want to have a semantic label and a instance label. For instance label, it's like there are a bunch of chairs, and we want to label chair 1 and chair 2. And instance segmentation and object detection has received a lot of attention these days, and it has some promising work in 2D. For RCNN, they have these region proposals. So we use similar concept that we propose similarity group proposal for 3D point cloud instance segmentation. It's an end-to-end trainable network for point cloud instance segmentation. And our network has 3 branches. The first one is semantic prediction, and then similarity matrix, and the confidence map. For semantic prediction, we want to have a probability vector for each point, indicating the probability of this point classified into object category. And then we want to build a similarity matrix for group proposals. And we want to compute pairwise distance in feature space for each point, and then build this n by n matrix. N is the number of points, and each row represents a group proposal. And suppose the similarity matrix is S, so Sij means the i's point and the j's point, the distance of them in feature space. And the thing is how we train this network. We have deep metric learning and CMS network. If 2 patches are similar, we want them to be similar, closer in feature space. So we adopt similar concept in our training, and we propose this double hinge loss. And for point I and point J, if they are in the same object instance, we want them to be similar in the feature space. And there are a lot of group proposals, so we want to prune them. So we further predict this confidence map. For confidence map, the ground truth is the IOU between SI and the ground truth of SI. So S is the similarity matrix. So in the visualization, the lighter color means lower confidence, so it mainly is the connection part. And we further do this group merging post-processing to further prune the result and get the final group predictions. And here are some results on Stanford 3D indoor data set. And the second line is, the second row is our prediction result. Here is a close-up of the result. We can see that our method can perform better than others. And also we have more result on other experiment, on other data set. And also, if you change the threshold for other method, they get bad result like the right column, and our method can identify each chair correctly. So if you are interested in our work, please come to our post session at D2. Thank you.
Hello, everyone. I'm Daniele. I'll introduce SPLATNet today. So reasoning 3D geometry is a fundamental problem in computer vision. Most existing methods represent 3D shapes using low-level elements, such as 3D points, small triangles, or per pixel depth values. These low-level representations are often hard to analyze and not application-ready. In this project, we try to reason high-level geometries. Given this image, we'll extract the entire floor as one surface. We'll also extract other surfaces, such as the background wall and the door. This surface-based representation is not only inherently smooth, but also enables many applications. From an input RGB image, we'll extract a set of planes. Each plane is represented by 3 parameters. Here we assume the maximum number of planes is 10, so we estimate 10 by 3 parameters, with some of them being empty. We also predict a 2D mask for each plane to define its scope. For non-planar regions, we predict per pixel depth values. We train a neural network based on dilated convolution to predict 3 types of information simultaneously. To define the loss, we find the matching between the ground truth set and the prediction set based on the distance in the parameter space. In addition, we allow some ground truth planes to be empty. We use the same matching to supervise the plane segmentation task. To further improve the reconstruction quality, we also add supervision on depth map synthesized from the plane parameters and masks. We fit 3D planes on 3D mesh models from the SPLATNet dataset and project 3D information to each camera view to generate the training data. Our surface-based representation enables many applications. With the detected planes, we can replace textures, say adding virtual TV screens. We can also create some virtual reality games. Here, we use the detected planes for physics simulation and render the input image as a background. With the reconstructed 3D geometry, we can also measure distance in 3D space. Here, we specify the starting point and the end point to draw a virtual ruler. Our reconstruction is in metric scale. Now let's look at more results. Here we show the input image, segmentation mask, synthesized depth map, and 3D models. Results show that our PLANET is able to extract mouse planes robustly. For baseline methods, we first infer per pixel depth values and run existing plane extraction algorithms. The blue curve shows that PLANET outperforms all baselines by a large margin. Our reconstructed depth map is not only inherently smooth, but also achieves the state-of-the-art performance in terms of accuracy. Finally, we want to note that PLANET learns a consistent ordering of planes without explicit supervision. With this property, we can denote room layout planes and use PLANET to estimate room layout. Our codes and data are available at our webpage. Thank you all for this.
Hello, I'm Shenlong from University of Toronto and Uber ATG. So in this paper, we present deep parametric continuous ConvNet, which is a joint work by a number of researchers in our lab. Unstructured data is everywhere in the world. We have a need to process it. For instance, the LiDAR point cloud perceived from self-driving cars. It has critical applications such as detection, motion estimation, segmentation, and mapping. Previous works can either convert those unstructured data to 3D or 2D gray data, or learn a deep set function over the whole data, or conduct convolution over predefined structure, such as 3D meshes. In our work, we develop a new neural network layer, which is conceptually very similar with convolution, but conducted over continuous domain. So how do we achieve that? Our motivation is behind the original definition of the continuous convolution, which is defined here in this equation. However, we cannot directly use that as a neural network layer. There are two major reasons. The first one is because of the continuous integration that happens, which is computationally infeasible. And the second reason is the generic kernel function, which spans the whole continuous domain, has infinite support. So in order to overcome these two drawbacks, we propose two major modifications over this. Firstly, we approximate our continuous integration using a local neighborhood. And secondly, we use multi-layer perceptron, which is finitely parameterized as our generic kernel function. This makes our continuous conv deep learnable again. Based on this layer, we build a neural network architecture that is end-to-end differentiable. It is applied on unstructured data over continuous domain with no geometric loss at all, and our input and output could be different. We verify our method over several challenging tasks. The first one is a LiDAR segmentation, where we achieve 10% higher IOU than the best competing algorithms. The video is going to show qualitative results of our method. The top is our ground truth, and the bottom is our prediction. So from this, we can see our method is able to capture both large objects, such as trucks, and small objects, such as pedestrians, really well. Next, we evaluate our method over LiDAR flow task, which estimates the 3D motion of each LiDAR point between 2 consecutive frames. Here, as we can see, our method outperforms the competing algorithms by a large margin. Here we show a video of the results. Top is ground truth, bottom is prediction, and each color represents different motion vector. From this video, we can see our method is able to capture both dynamic objects motion and the motion caused by the ego car, both really well. And finally, we apply our method over the Stanford indoor segmentation task, where achieve 11 percentile yield higher than the state-of-the-art method, and our inference runtime is only 66 milliseconds. In conclusion, we propose a convolutional neural network directly over unstructured data and verify our results on segmentation and motion estimation. Please do try our continuous conf if you are tired of building a Minecraft-like world before applying your CNNs. Thank you.
everyone. I'm going to present you our paper, Image Collision Pop-up. In the last decades, many efforts have been done in the structure for motion field. Remember that this problem consists in recovering the 3D reconstruction of an object, and the camera pulls from a collection of images. To do this, we have to establish point correspondences between images, even considering partial observations, in order to infer a unique 3D model. More recently, this problem is extended to the non-rigid domain, and many solutions have been proposed in non-rigid structure for motion. Again, using a similar input data, in this case, we can recover a time-varying 3D model. This means we have a different 3D configuration per image. In both previous cases, single object instances are processed. In contrast, in this paper, we propose a novel technique for multiple instance reconstruction. Thanks to this new paranoid, we can process a wide variety of categories, such as cars, doors, trains, and others, using semantic point correspondences. In this paper, we use consider three scenarios. First of all, we analyze a collection of images where rigid objects appear. For example, in this case, we have the same object in two different pictures. As you know, only the camera pose is different for every image. However, when we include more images, even the 3D model can change due to a deformation between object instances. Secondly, we can consider also non-rigid objects, such as faces. In this case, we can find a deformation between object instances and a linear deformation between faces of the same instances. And finally, we can extend our observation to nonlinear deformation, such as the articulate motion of humans and animals. In this more general case, we can use three components to code the 3D configuration per image. So our approach to multiple instant reconstruction can only recover 3D reconstruction, camera pulse, and clustering. To this end, we introduce the concept of multiple universal subspaces. Our approach is unified and supervised, doesn't require any training data at all, can handle missing correspondences, and can group the image into different modalities. We formulate this problem in terms of augmented Lagrange multipliers, proposing an energy-based problem. In addition, we add 4 constraints to consider the projection equation, the orthogonality constraints in the camera rotations, and a couple of union and subspaces to consider both rigid and non-rigid categories. We validate our approach on synthetic collection of images, obtaining the best performance in terms of reconstruction and clustering. In addition, we also observe our approach provides robust solutions against noisy observations. Here, let me show you several samples of our estimation on bicycles and chairs. On the other hand, we also use our approach to multiple instance phase reconstruction. Again, our approach obtains nice results in terms of clustering and reconstruction, even for structure missing data due to self-occlusions or lack of visibility. Note that in this case, our method has to estimate both 2D and 3D locations. To finish with, we also validate our approach on articulate motion, in this case on dogs reconstruction. Here. And again, let me show you several samples of our estimation. So hope to see you in our poster section, and thank you so much.
Hi, I'm Samart Brahmbhatt, and I'm going to present our work on camera localization, which is a collaboration between Georgia Tech and NVIDIA. So recovering the 3D position and orientation of a camera is an important vision problem with applications in AR, autonomous cars, and robotics. Our algorithm MapNet localizes a camera in a known scene using an RGB image. A good map representation is essential for localization. Various representations have been used in the literature, like point clouds with 2D features, 3D meshes and volumes, and plain lines and other primitives. In MapNet, we take a data-driven approach where it is inspired from the PoseNet line of work, where map information is stored implicitly in the weights of a neural network. However, we are able to learn a better performing and more interpretable map, as we'll see later. All these algorithms need labeled data in the form of image camera pose pairs, which is quite expensive to collect, so there's only a limited amount. On the other hand, unlabeled data, which is in the form of videos collected from the same scene, can be easily collected, and we have lots of that lying around. Unlabeled data is obviously less informative, but creatively using it can significantly improve performance. While some labeled data is always needed, the more unlabeled data you use, the better MapNet becomes. Let's look at how to train it. So we first take some labeled data and sample tuples of nearby images. These are fed through a CNN which predicts absolute poses. In addition, we also compute the relative transformations and combine them in a loss function that is supervised by both absolute and relative pose ground truth. This algorithm, which utilizes constraints between pairs of images, is called MapNet. Now, if we have unlabeled video data, we can fine-tune a trained MapNet model and improve it. Again, we sample tuples of nearby images and combine them with some labeled images to make a mini batch, feed them through the MapNet, and the relative pose predictions between these unlabeled images are used in an additional loss function LT, which is supervised by off-the-shelf visual odometry algorithms. Absolute translation predictions can also be used if we have weak labels in the form of GPS data. This algorithm, which efficiently uses unlabeled data to improve MapNet, is called MapNet Plus. We also use moving window pose graph optimization during inference, which incorporates relative pose constraints from visual odometry to produce smooth and drift-free camera pose estimates. Okay, let's look at some experiments on indoor data. On the 7 scenes dataset, MapNet significantly improves performance compared to other learning-based methods and visual odometry, both for camera translation and orientation. And here's an example result from the red kitchen sequence in 7 scenes. We observe the same trend on outdoor data from the Oxford robot car dataset, also for the small loop sequence and the large 10-kilometer full sequence. Here are some results on the Oxford robot car dataset. How useful is more unlabeled data? This graph shows that more of it continues improving performance, but obviously its impact is smaller than that of more labeled data. This trend holds for translation as well as rotation performance. And if we look at attention heat maps, we can see that MapNet concentrates more on geometrically meaningful regions like edges, both indoors and outdoors. And its attention is also more consistent temporally. Thank you for listening, and you can access our code and models at this website, and we hope to see you at Poster D17. Thank you.
Hi, my name is Jiang. I'm here to present our paper, Recurrent Slice Networks for 3D Segmentation of Point Clouds. In this paper, we are attacking the problem 3D segmentation on point clouds. This problem is challenging because it's really hard to apply traditional end-to-end deep networks to unordered and unstructured points. So many existing works use like something like 3D volumes so that you can apply 3D CNN to that. And however, it's really very slow, and there may be some information loss in the voxelization stage. And some other methods used direct point clouds as inputs. For example, PointNet. PointNet is working great, but there's no local structure modeling in PointNet. As we all know, local structure modeling is crucial for segmentation tasks. In PointNet++ and KDNet, they do have like local structure, some kind of local structure modeling in their methods. However, they require too much computations to do that. This makes them like their algorithms much slower. So in this paper, we are presenting RSNet. RSNet supports local structure modeling, and more importantly, it's computationally efficient. That means we can apply RSNet in real-time applications, and I'm going to show that later. So the key part of RSNet is this local dependency module, which consists of slice pooling, RN, and the slice unpooling layers. So slice pooling is designed to project unordered points to an ordered and structured sequence so that we can apply RNs to model the dependencies in this sequence. And at the end, we are going to use slice unpooling to project features from RNs back to the each point in the input so that we can make final predictions for these points. We benchmarked the performances of RSNet on the large-scale 3D indoor spaces datasets, and we compared against Cloud, which uses 3D CNN and PointNet. And without using any data augmentation or conditional random fields, our method is able to achieve new state-of-the-art performances. And after that, we also compared against PointNet++ on the ScanNet dataset, and RSNet is able to significantly boost the segmentation performances on this task. We achieved much higher mean IOU and mean accuracy. And we also compared with a bunch of other algorithms such as KDNet on the ShapeNet part segmentation task. And when not using the normal information, our algorithm is able to achieve state-of-the-art performances. So as I mentioned before, RSNet actually is very computationally efficient. It's much faster than its counterparts, PointNet++. However, it even requires less GPU memories than vanilla PointNet. That means we can apply RSNet to some real-world applications. And here are some visualizations of outputs from RSNet. We can see that RSNet is able to do a great job at most of the cases. And if you have any question about our paper, feel free to come to our poster session. And if you are interested in challenging problems like 3D segmentation and 3D detection in self-driving, come and join us. Thank you.
This is Sanxin from Imperial College. It's a great honor to be here to present the work. I'm very grateful to my co-authors for making this work possible. So you can see we have a lot of collaborations. Last year, we organized a challenge to do the 3D hand pose estimation for 3 scenarios, okay? Frame by frame, continuous tracking, and hand object interaction. And we analyzed the top 10 method to see the current state and also the future challenges in this area. And we divided this method into different categories and using different the following criteria, like, for example, the method using hand structure, or it's a one stage or multiple stage, or it is does it using ResNet. The full taxonomy of the work is like this. So depending on the visibility of the joint and also whether the hand shape is in the training data or not, we divided it into 4 cases. The easiest one is a seen visible joint in the seen hand shape, and the most challenging is the occluded joint in the unseen hand shape. We have different, the overall performance is 60% of the maximum jaw error within 20 millimeter and average of 70 within 10 millimeter error. The current method is still have a big gap between the perfect performance. Also, the worst case is the occluded joint of the new hand shape. So for 3D CNs generally outperform the 2D CNs, even though they have a similar structure. And our detection-based method, it outperforms the regression-based method in general. And we also analyze the different structures, how to include the structure into the CN networks, and also the multiple state method, it outperformed the single state method. We analyzed the joint visibility along with a number of visible joint. It can the error, the performance increases along with the number of visible joints. For the viewpoint distribution from one extreme case to the other end of visible case, they kind of like in the extreme viewpoint, we have worse performance in the common viewpoint. For the articulation, for the open palm to the other end of the foley and fist, it's like the error distribution is like this. For the tracking, we also analyzed the detection accuracy as well as of the hand pose estimation accuracy. For the object interaction, we discussed the different cases as well as for different joint. The take-home messages like 3D volume is better than 2D representation, and detection-based is good, but regression-based method and plus the spatial constant can also have very good performance. For the hand structure, can help deal with the occlusions, and by integrating the hand model, it seems promising to deal with unseen hand shapes. And also, multiple stage is better to deal with extreme viewpoints. For the tracking, we kind of how to use the initialization in the initial frame is very pursuing. And for the object, we had tried segmentation and better data. Thank you.
Hello everyone, I'm Mira Slavcheva and I'm going to talk to you about our new method for 3D reconstruction of scenes undergoing free non-rigid motion called Sobolev fusion. It was created with Max Baust and Slobodan Ilic from the Technical University of Munich and Siemens Corporate Technology. Our objective is a real-time method that reconstructs surfaces captured with a single RGBD camera while moving. We aim at handling truly arbitrary everyday scenes, including fast motion, multiple interacting subjects, and the resulting topological changes as shown here. Moreover, we want to be able to color the output reconstruction and enable tasks such as texture transfer and character animation. Previous work goes in two directions. Dynamic fusion-like methods track and reconstruct the surface under a correspondence-based warp field, achieving ever-improving quality. However, fast motion is a challenge, and topology changes can only be circumvented via key volume reinitializations. Conversely, our previous work, Killing Fusion, warps sign distance fields using the variational level set method, which handles changing topology and large motion, but loses data association. Moreover, its combination of regularizers may lead to oversmoothing. As we believe that this strategy is better suited to capturing arbitrary geometry, we aim to improve geometric detail and add voxel correspondence. So our pipeline takes in a single RGBD stream and uses a modified gradient flow to warp the projected TSDF of each frame towards the canonical model and fuse it. Then it determines voxel correspondences in order to also fuse color. Our flow energy consists of a data similarity term and a motion smoothness regularizer. Instead of using gradient based on the standard L2 inner product, we project it to the smoother Sobolev space H1 by applying a 3D convolution. This leads to gradient descent, which is less susceptible to local minima without changing the global optimum. Furthermore, it exhibits a coarse-to-fine evolution behavior, where global deformations are recovered before smaller scale details, as shown in this 2D example. To keep interactive frame rates, we split the 3D kernel into 3 1D filters via higher order SVD decomposition. Then we transfer color from the initial to the warp TSDF using the lowest frequency eigenfunctions of their Laplacians as they encode inherent deformation patterns. We match the eigenfunctions by considering them as histograms and then convert to voxel coordinates via nearest neighbor search. This strategy recovers a sparse set of correspondences which become smaller with frame distance and can be densified through an expectation maximization procedure, but due to its slowness, we do not employ it and fully color only the output reconstruction. We begin our results with a sequence of a person turning in a complete loop while playing with a balloon. Even in the presence of this splitting emerging geometry, we obtain a complete textured reconstruction. Next, we compare to Killing Fusion. While results are similar due to the common energy, the introduced Sobolev gradient flow reduces oversmoothing. It also better captures concavities and defines sharper edges. Here we see that both volume deform and Killing Fusion tend to fuse the strap into the umbrella surface, while Sobolev fusion better separates the structure. Finally, quantitative evaluation on ground truth canonical models demonstrates that the improved gradient flow also leads to improved geometry. So we have fulfilled our goals for sharper details and recovering correspondence in level set-based non-rigid reconstruction. In future, we will switch to a hierarchical data structure in order to handle larger volumes and aim to determine a denser set of correspondences. So thank you for your attention, and come to poster E for further details.
Hello everyone, I'm Jogendra. I'm going to present AdaDepth unsupervised content congruent adaptation for depth estimation. This is a joint work with my colleagues Fani, Anuj, and my advisor Dr. Venkatesh Babu at Indian Institute of Science. For monocular depth estimation, the ground truth acquired using devices like Kinect or other depth sensors, for example LIDAR, etc., exhibit noisy artifacts. Hence, it severely limits the performance of supervised depth prediction networks. In the other hand, depth maps generated from synthetic environment is much more clean and accurate. Therefore, we plan to adapt learned representation from clean synthetic image depth pair to real natural scenes. Available adaptation methods are mostly limited to classification setup and do not scale well for fully convolutional architectures. Major challenge in such architectures is to preserve the spatial structure of the high-dimensional encoded feature in absence of paired samples from the target domain. Such models often leads to mode collapse without an efficient content consistency regularization technique. In our approach, the base CNN encoder-decoder architecture is divided into two transformations, MS, that transforms an image to the latent representation, and T, that transforms the latent representation to the final depth prediction. We employ two different discriminators, DF and DY, as shown in the figure. The adversarial loss from DF tries to minimize the domain discrepancy at the encoded latent representation, whereas the adversarial loss from DY tries to align the predicted depth with the actual depth distribution. We experimented various content regularization techniques, first of them being domain consistency regularization, DCR. Assuming resultant adaptation as a small perturbation, we enforce L domain regularization in the adversarial objective. Experiments with various weight sharing strategies reveal that adapting only Res5 block of ResNet 50 encoder gives improved adaptation performance. As a new approach to preserve spatial structure and content correspondence, we propose to enforce content consistency using a self-feature reconstruction loss. We define CT as a parameterized feature reconstruction function which can reconstruct back the Res4F features during the adaptation process. Interestingly, our unsupervised adaptation model, AdaDepth U, is able to deliver comparable result against a previous state-of-the-arts. Additionally, with semi-supervised setting, AdaDepth S outperforms previous fully supervised monocular depth prediction methods. For indoor scenes, we consider adaptation from synthetic PBRS to natural NYU depth dataset. For outdoor scenes, we adapt model learned from synthetic VKitty to standard Kitty dataset. Similar trend in result is observed in the Egan split of Kitty dataset as well. In summary, AdaDepth works on high-dimensional structured encoded representation. It addresses mode collapse by enforcing content consistency regularization in the most effective fashion. Finally, the two discriminators help to bridge the domain discrepancy underlying both marginal and conditional distribution, which is crucial for domain adaptation. We have made the code and models available publicly. For more details, please come to our poster number E7. Thank you.